A lot of students think that Le Chatelier's principle is infallible. It is always correct, but that's not going to be true. And we're going to see a few examples today in this video to prove that. Now I'm going to start this video out by showing just some general times when Le Chatelier's principle can fail. And then we're going to dive into one of these general types of exceptions, and we're going to explore it in more depth with examples. But I want to provide multiple ways it can fail just to teach you as much as I can. So one way Le Chatelier's principle can fail is when we're adding finite amounts rather than infinitesimal amounts. Another way this principle can fail is when we have an open system. Sorry, that's really bad handwriting. Another way this principle can fail is when we're measuring the solubility of an inorganic salt with temperature, with respect to temperature. Actually, I should mention here one kind of super important exception that actually is one of many students' first intros to equilibrium is actually, it's the ammonia synthesis. Process. This actually is an exception to Le Chatelier's principle when we add finite amounts, and there's research on that you can search up. But today, I want to focus on teaching you the last way I'm going to mention, which is when we have different moles of gas on each side of the reaction. And really, this kind of exception deals with two big ones. There's two cases in which this is true. It's when we have constant pressure or a non-rigid container. And oftentimes we're going to see that the non-rigid container, really that's just to facilitate that constant pressure. Okay, so enough talking. Let's get into some examples now. So example 1, we have CS2 gas plus 4 hydrogen gas. And that's in equilibrium with methane gas and 2 hydrogen sulfide gas. Okay, so important kind of conditions of this reaction is 1, we have a movable piston. That's the condition, that's the environment. And we are also at a constant temperature and pressure. So understanding those conditions, let's ask yourself, what happens if we add a bit of CS2, if this goes up? So Le Chatelier's principle would predict, the CH4, if we're trying to predict what will happen to the methane, Le Chatelier's principle would predict that the methane is going to increase. And really, that's a not very nuanced way of looking at it, and we're going to dive into that here. So the way you're supposed to solve this with the constant temperature and pressure is looking at the equilibrium expression, okay? So if you write it out here, our QC can equal, and actually C is an important thing too. A lot of people with gases, they instinctively go towards Kp. But here QC is actually going to be our friend. And remember, because we have a volume and moles of gas, you can represent it as a concentration. So we're going to have, if you write it out, concentration of methane times the concentration of H2S, that's going to be squared, over the concentration of CS2 times the concentration of H2 gas to the 4th, right? So, but really, if we remember, molarity is just moles over volume. So this expression is equivalent to the moles of methane over the volume times moles of hydrogen sulfide over the volume squared, divided by, now we have the moles of CS2 over the volume times the moles of hydrogen over the volume, and that's to the fourth. And okay, we can go even further from here. Let's separate the moles and the volume terms. So this equation is also equivalent to the following. So if we have just the moles of CH4 times the moles of H2S squared over the moles of CS2, and then times the moles of H2S squared. Oh my god, sorry, I wrote that twice. The moles of H2, that should be to the fourth, okay? So, sorry about that. So, that, remember though, we also have the volume term here. So, here we really have 1 over V times 1 over V squared times, or divided by 1 over V times 1 over V to the fourth, okay? So these are equivalent, and if we look at this volume term, really, it reduces down to 1 over V cubed over 1 over V to the fifth. And if you remember your exponent rules, that's because we're adding these here, and when we divide it, they're subtracting. So really, this whole expression is equal to 1 over V to the negative second. And that, once again, is equivalent to V squared. So this whole big thing is equal to all these moles times V squared. That's really the big kind of important part we realize here. Now, normally this might not matter, but remember that we have, I'm going to circle it for emphasis, we have a constant temperature and pressure. That's super important. So because of that, what that means is if we add more moles of CS2, the volume has to increase, right? How else would the pressure, be constant, temperature and pressure? The volume must increase here. However, remember that the moles here in the denominator are increasing. So really, we can't determine whether the methane is going to increase or decrease at all times, because our QC could be greater than the KC if, let me pull up my notes here. It could be greater if this ratio of volume squared over these moles, if that is greater than the initial. It's greater than initial, because then our QC would be greater than KC. We'd increase that, and then the reaction would shift backwards. And in contrast, if our QC is less than our KC, that would be because this term is less than initial. So now, if you think about this, really the correct answer here is that it depends on the initial amount. It depends on the initial amount of CS2. This is the correct answer. So, moving on, we're going to go to number 2. So, you're going to see kind of the process we go through is going to stay the same, but the conditions are going to differ. So, we're going to have carbon monoxide gas plus 2 hydrogen gas. And that's going to be in equilibrium with methanol. Gas once again. So when we look at this question now, we're going to do, once again, movable piston. And this time, we're also going to once again have constant temperature. I'm going to just do T and P. Okay. So now, this time, instead of increasing the reactants, we're going to add argon gas. Whoa. So LCP, Le Chatelier's principle, would predict that the this wouldn't change anything. It's an inert gas. But actually, we're going to realize that's wrong because of, once again, constant temperature and pressure. So let's do this problem. So if we look at the same kind of setup here, if we do the same as above, we'll end up getting, we have this many moles of methanol over the volume divided by the moles of carbon monoxide divided by the volume times moles of hydrogen gas over the volume squared, and that this is QC, and our QC is equal to the moles of methanol over the moles of carbon monoxide times the moles of hydrogen squared times 1 over V divided by 1 over V cubed. I'm just adding these exponents here, the invisible ones, and that this term is equal to, actually, 1 over V to the negative 2, which is actually equal to V squared. Now, it's just a coincidence here that our 1 over V's, or that we end up with V squareds. That's not always going to happen, but that just happened to happen. And when we look at this, let's think of it as, again, argon, constant temperature and pressure, movable piston. How can the volume change? Will it change? Yes, it will, because we're under constant pressure. So our volume here is going to increase. Volume is going to increase. So what does that mean for us? That means our Q actually is going to be greater than our Kc, because this QC is equal to this V is equal to this moles times V squared term, and our V squared is actually increasing. So our QC is going to be greater than our Kc. So actually our reaction is going to shift to the left. And that is unlike what Le Chatelier's principle said. It said nothing would happen. So finally, we're going to look at problem number 3 here. Problem number 3, we're going to have N2O4 gas. And that's kind of in equilibrium here with 2NO2 gas. Super common dimerization reaction. So this is in a syringe. And when you think about it, a syringe is just a fancy way of saying a movable piston, like we had in problems 1 and problems 2. So other thing we have here is our volume is going to decrease at a constant temperature. Okay, and that's going to be done by moving this plunger in the syringe. So we're trying to figure out the concentration of NO2 here, okay? So we'll see there's kind of a twist here because of constant temperature. So what we're going to do here is we're going to do kind of the same process once again. Sorry, give me a minute. Same process. So the moles of NO2 over its volume, that's squared divided by, this is equal to QC, and that's equal to the moles of N2O4 divided by the volume. I guess that's the first you can say. And that's equal to moles of NO2 divided by the moles of N2O4 times 1 over V squared divided by 1 over V So this term is equal to 1 over V. So really our equation that we have is this moles term times 1 over V. Okay. So now let's say this. Our volume decreases, right? So typically just as we did in the past two, we'd say, okay, volume decreases, but this term is the inverse of the volume. So really what's happening is this term as a whole is, I'll do that in red. The term as a whole is increasing. This is a bad arrow, but hopefully you can see that despite the fact that the volume is decreasing, it's the inverse of the volume. So that term as a whole increase. Okay, so you might expect me to say, oh, QC will increase, so QC is greater than KC, which is true. That is true. I don't know why I said you might expect that, because that is true. You should expect that. But our kind of ruffle here is not that it only goes backwards. Is that, remember, constant temperature. Kc can only be changed by changing the temperature, or K can only be changed by changing the temperature. So if temperature is constant, Kc must be constant. Right? And if, remember, we're shifting, because QC is greater than KC, we're shifting to the left, We're increasing the volume of the amount of N2O4. But that means Kc is different. And if you want to keep Kc constant, we have to increase the amount of NO2 as well. So kind of to summarize that, if we want to keep Kc constant, the concentration of NO2 in the new equilibrium mixture must be higher than that of the initial equilibrium mixture, because the amount of N2O4 molecules is going to increase in the new equilibrium mixture. So what actually ends up happening here is both the N2O4 and the NO2 increase, which is kind of weird, but I think it's cool that a lot of these things that Le Chatelier's principle oversimplifies actually have a lot of more interesting solutions here. So both concentrations increase here. And in the second case, it shifts to the left despite having the inert gas. And in our first example, it actually depends on the initial conditions. So I hope this kind of convinces you as a whole when I kind of zoom out here. I'll zoom back into our initial stuff. But to be a bit more careful when you use Le Chatelier's principle, not just use it as like a bandage and like a cure-all, really. You should be carefully done, and I think it's important to remember the use of our reaction quotient as shown in the bottom examples. So I hope you found this informative. I wish you best of luck with your future chemistry.